Rainbows are natural optical phenomena, appearing in the sky after rainfall. Rainbows are formed by sunlight, refracting and reflecting within water droplets. The full color spectrum is visible due to the varying angles of refraction for each wavelength of light. Rainbows always appear opposite the sun from the observer's perspective. A rainbow is a continuous arc, but it often appears incomplete due to the horizon. Double rainbows can occur when light reflects twice inside the water droplets. Rainbows are formed through the refraction and reflection of sunlight within raindrops. Refraction occurs when sunlight enters a raindrop and bends due to the change in medium. Reflection happens when the light bounces off the inner surface of the raindrop. The separation of white light into its constituent colors is due to different wavelengths refracting at slightly different angles. Refraction and reflection within water droplets separate white light into its constituent colors. Refraction occurs when light bends as it passes from air into water due to the change in speed. Reflection occurs when light bounces off the inner surface of the water droplet. The separation of white light into different colors is due to the varying wavelengths of light experiencing different degrees of refraction. Light refraction separates white light into its constituent colors. The angle of refraction varies for each color, determining its position in the rainbow. Rainbows are formed when sunlight is refracted and reflected by water droplets. The specific arrangement of colors in a rainbow is due to the consistent angles of refraction and reflection. A primary rainbow is formed by the refraction and reflection of sunlight within water droplets. The colors in a primary rainbow are arranged in a consistent order: red on the outside and violet on the inside. A secondary rainbow can sometimes be observed outside the primary rainbow. The color order in a secondary rainbow is reversed compared to the primary rainbow. The reversed color order in a secondary rainbow is due to a double reflection of sunlight within the water droplets. Secondary rainbows appear fainter than primary rainbows because of the additional reflection, which reduces light intensity. Rainbows are subjects of myths and legends across various cultures. In Irish folklore, a pot of gold is often said to be found at the end of a rainbow. Australian Aboriginal mythology features the rainbow serpent as a creator being. These myths often reflect cultural values and understandings of natural phenomena. Rainbow legends demonstrate humanity's enduring fascination with natural wonders. In some mythologies, the rainbow serves as a symbolic bridge or pathway to another world. The rainbow's vibrant colors often represent a connection between the earthly and the divine realms. Myths often depict deities or spirits using the rainbow to travel between worlds. The rainbow symbolizes hope, transformation, and the potential for transcendence. The legend tells of a pot of gold located at the end of a rainbow. The rainbow's apparent end is an optical illusion dependent on the observer's position. As the observer approaches, the perceived end of the rainbow recedes at the same rate. This perpetual recession makes the pot of gold at the rainbow's end perpetually unreachable. The legend serves as a metaphor for unattainable goals that seem perpetually within reach but always remain elusive. Across cultures, the rainbow frequently symbolizes hope and new beginnings. In some societies, the rainbow represents a divine promise or covenant. The rainbow is often seen as a harbinger of good fortune and positive outcomes. Cultural interpretations of the rainbow vary, reflecting unique societal values and beliefs. Moonbows, also known as lunar rainbows, are rare optical phenomena similar to rainbows but produced by moonlight. Moonbows form when moonlight refracts and reflects through water droplets in the air, much like rainbows formed by sunlight. Specific conditions are required for moonbows to form, including a nearly full moon, a dark sky, and moisture in the air. The faint light of the moon often makes moonbows appear white to the naked eye, though colors are present. Moonbows are most commonly observed near waterfalls or during or after rainfall at night. Rainbows can form near waterfalls due to the presence of water droplets in the air. Sunlight is refracted and reflected by water droplets, separating the light into its constituent colors. The angle between the sunlight, the observer, and the water droplets must be approximately 42 degrees for a rainbow to be visible. Other sources of water spray, such as garden hoses, can also create rainbows under the right conditions. Rainbow formation is dependent on the observer's position relative to the sun and raindrops. Each observer perceives a unique rainbow due to the specific angle at which they view refracted and reflected sunlight. The angle of maximum intensity for rainbow formation is approximately 42 degrees relative to the incoming sunlight. No two observers can occupy the same spatial point. Therefore, each rainbow is unique. Rainbows are not physical objects, but optical phenomena, dependent on the observer's perspective. The perceived location and shape of a rainbow change as the observer moves. Rainbows form when sunlight refracts and reflects within water droplets. The observer sees a rainbow when looking at water droplets opposite the sun. Rainbows appear as arcs because of the constant angle between the sunlight, water droplets, and the observer's eye. The center of the rainbow's arc is always directly opposite the sun from the observer's perspective. Under specific atmospheric conditions, a full circular rainbow can be observed from an airplane. The full circular rainbow is formed by light, refracting and reflecting within water droplets. Unlike ground-level rainbows, the airplane's altitude allows for the entire circle to become visible. The center of the circular rainbow aligns with the shadow of the airplane. Atmospheric conditions such as cloud density and sunlight angle contribute to the rainbow's visibility. Rainbow intensity is directly influenced by raindrop size. Larger raindrops produce more intense and vibrant rainbows due to increased light refraction. Sunlight strength is a crucial factor affecting rainbow clarity. Stronger sunlight leads to brighter and more defined rainbows. Optimal conditions for rainbow formation require both large raindrops and strong sunlight. Variations in raindrop size and sunlight strength can result in different rainbow appearances. Rainbows require both rain and sunlight to form. Sunlight must strike raindrops at a specific angle to create a rainbow. The spectrum of colors in a rainbow is created by the dispersion of sunlight within raindrops. Rainbows always appear opposite the sun from the observer's perspective. Supernumerary rainbows are faint bands that appear inside the primary rainbow. These bands result from interference effects involving sunlight with similar path lengths. The size of water droplets influences the spacing and intensity of supernumerary bands. Uniform droplet size is crucial for the formation of distinct supernumerary rainbows. Interference patterns cause constructive and destructive interference, leading to visible bands. Supernumerary rainbows demonstrate wave optics and light interference in atmospheric phenomena. Rainbows are meteorological phenomena caused by reflection, refraction, and dispersion of light in water droplets. Fogbows, also known as white rainbows, occur when sunlight interacts with the smaller water droplets in fog. Unlike typical rainbows, fogbows exhibit weaker colors due to the small droplet size. Circumhorizontal arcs are ice crystal halos formed by refraction of sunlight through horizontally oriented ice crystals in high-altitude cirrus clouds. Circumhorizontal arcs require specific sun and cloud alignment to form. The orientation of ice crystals dictates the color separation and appearance of circumhorizontal arcs. Spectrometers are used to analyze the wavelengths of light present in rainbows, revealing their spectral composition. Polarimeters measure the polarization of light in atmospheric phenomena, providing insights into particle size and orientation. Rain gauges and weather balloons collect data on atmospheric conditions, such as humidity and temperature, that contribute to rainbow formation. Cameras equipped with specialized filters capture high-resolution images of rainbows, documenting their structure and intensity. Data from multiple instruments are integrated to create comprehensive models of rainbow formation and atmospheric optics. Rainbows can serve as indicators of imminent weather changes. A rainbow appearing shortly after rain often suggests that the weather will clear up quickly. Conversely, a persistent or intensifying rainbow might indicate continued unsettled weather. Observing the position and intensity of a rainbow can provide clues about approaching weather systems. Rainbow formation involves the refraction of sunlight as it enters a water droplet. Internal reflection within the water droplet further separates the colors of light. Diffraction causes the light waves to spread out as they exit the water droplet. Interference between light waves intensifies certain colors, creating the distinct bands of a rainbow. The angle of observation relative to the sun and raindrops is crucial for seeing a rainbow. Rainbows are observed as arcs because of the spherical shape of raindrops and the consistent angle of refraction and reflection. Rainbows have been a recurring motif in art, symbolizing hope and beauty across cultures. In literature, rainbows often represent a bridge between the earthly and the divine, or a promise of better times. Popular culture frequently uses rainbows to signify diversity, inclusion, and celebration. The rainbow's visual spectrum is often used to represent a range of emotions and experiences. Historically, rainbows have been interpreted as symbols of good fortune and divine connection. The human eye perceives color through specialized photoreceptor cells called cones, which are sensitive to different wavelengths of light. When white light passes through a prism, it is separated into its constituent colors due to refraction, creating a rainbow effect. Each color in the rainbow corresponds to a specific wavelength of light, ranging from red, longest wavelength, to violet, shortest wavelength. The rainbow effect demonstrates how the human eye and brain interpret different wavelengths of light as distinct colors. Rainbows are optical phenomena caused by refraction and reflection of sunlight in water droplets. Sunlight enters a water droplet, refracts, reflects off the back, and refracts again as it exits. The different wavelengths of light are bent at slightly different angles, resulting in the separation of colors. A rainbow appears as an arc because of the constant angle between the observer, water droplets, and the sun. Rainbows hold cultural significance, often symbolizing hope, promise, and good fortune across various cultures. Double rainbows occur when light reflects twice inside the water droplets, reversing the order of colors. A vibrant rainbow arcs across the sky, showcasing a spectrum of colors. The rainbow's arc represents the refraction and reflection of sunlight through water droplets. The sequence of colors in a rainbow is consistent: red, orange, yellow, green, blue, indigo, and violet. Rainbows evoke a sense of wonder and beauty in natural phenomena.